Welcome to today's GEOTOP A webinar. Our speaker today is Armajac Pujol. He'll tell us about simplicial complexes and the index lemma, a pathway to reach agreements fairly. Take it away, Armajac.
Many thanks. First of all, thank you for the invitation in order we can share with you our work. This is a work of how to apply topology in a very specific problem in social choice. And we are working together with Sergio Raxbaum, that is a prominent researcher in distributed computing. And I'm a mathematician working on mathematics applied to economics and political science. So what is this about? So social choice is an area that studies how to make collective decisions taking into account individual preference or individual situations. For example, it studies the voting rules. It studies how to distribute shares of resources among different groups having different preferences. It studies auctions and so on. And one of the drawbacks is that the math that we use in this area usually is mainly combinatorics, and sometimes when we have a lot of options, when we have many objects to decide, things can go very complex, and sometimes we lose the intuition. And this is where topology can be is useful to us. In particular, we have started to use combinatorial topology. That, broadly speaking, it is the study of topological spaces using combinatorial properties of the triangulation of such spaces. So my talk, I have divided it into parts. The first part, I will introduce you the problem and present you the solution based in topology that we are applying. And in the second part, I will go deeper on the maths, and I will discuss why this approach is as useful to us. So let's start with the problem. Imagine that we are in a parliament or in the board committee of a company, and we have to decide between apply a policy A or a policy B. So in order to decide, I suppose that the first idea that goes in your mind is voting. In fact, a specific rule of voting, that is the majority rule, that as I hope you know, it means the policy I is applied if more people agree with the policy A than the policy B, and the same for the B. And in fact, this method of decision is quite good, because in 1952, May proved that this decision rule, the majority voting, is the unique rule satisfying these three good properties. The first one is anonymity. That means that A and B are symmetric with respect to the rule. The second one is neutrality. That means that there is a symmetry between all the voters. And positive responsiveness means that, for example, if we have a combination, a combination of voting that gives that the verdict of this voting is A, then if one vote goes from B to A, then the winner have to continue being A. So the direction of change of verdict has to be in the same direction that the change of number of votes. And the bad news is that this works when we only have two options, in this case A and B. And when we have more than two options, for example 3, some problems arise. For example, imagine that we have three parties, the party blue, the party red, and the party green, and the voters have these three possible preferences. 1/3 of the voters prefer B over R and over G, another third G over B and over R, and the third this one. So if we look for the majority rule, we can see that there is a tie between the three options. So there is no way to decide. And we can say, okay, there is not a way to decide in this way, but we can prove another solutions. And the second one is maybe we can compare by pairs what's happening. And we can see that, for example, if we compare the red party and the green party, red wins to the green party because 2/3 of the voters prefers R over G. And we can do the same with the green and the blue, and green wins to the blue because also 2/3 prefer green to the blue, and the same with the red and the blue. So the first solution of majority rule doesn't work. The second solution of comparison doesn't work. So maybe this is a complete a tie, and we have to agree with that. And well, it doesn't matter. But we can go deeper with another example and consider this one. We have here three distributions of preferences. The first one with 40%, the second one with 25%, and the third one with 35%. And in this case, if we apply the majority rule, we can see that the blue party is the one that will win. But if we go by comparison by pairs, as before, we can see that in fact green wins to the red because this the 65% prefers green over red, but green also wins to the blue because greens to the blue, yeah, this one 60% prefer greens to the blue, and the same with red and blue. So taking into account this diagram, G, the green party will be the most preferred party because it will win to every other party. So we have arrived in a situation in which the less voted party is in fact the party that will win. So the conclusion of these examples is that making decisions when we have more than three alternatives or three candidates is not as easy as we can think, and the resolution can depend on the voting method that we are using. So in front of these kind of problems, the researchers in the past century tried to define a global field in order to be sure about which one was the best decision mechanism they want to use, and which are the properties, and they try to find the best mechanism satisfying certain properties in order to be sure that this mechanism was the most democratic or the most fair or so on. So they decide to move the problem into an abstract level, and they consider that this framework, we have a society of n individuals, each individual have a preference, and we want to study functions that, given this n preference and input, provides us a preference representing the society. So basically they look functions like that, where B is the set of preferences that satisfy certain good properties. And the good properties can depend on the problem, can depend on the ethics of the collectivity, and so on. But the important point is find functions that satisfy desired properties. And this is where we arrive in our specific problem that we are solving. at least at the beginning of our problem. And one of the most important models for decision making, and probably one of the first, was the model proposed by Arrow. Arrow supposed that the preferences were represented by, or were modeled by strict orders, that is, a ranking without ties of the distinct options or alternatives that we have, and they look for functions that satisfied three basic properties. The first one is the Pareto property. That means that if all individuals agree that X is better than Y, then the social preference also marks X as better than Y. That it's quite reasonable. The second one is a little less intuitive and says that the social preference between a pair of alternatives only depends on the individual preferences on the same pair of alternatives. And this property is motivated by the idea of rationality that the researchers had at that time, that says that a decision between two options have to be made taking into account only the properties of these two options, or the attributes of these two alternatives. So it doesn't make sense that if we have to decide between X and Y, the properties or the preferences among a third alternative Z plays any role on this decision. And this is the origin of this property called independence of irrelevant alternatives. And the third one is again quite natural and says that no individual can decide over the whole society. So Arrow said that a good aggregation function had to satisfy at least these three properties in order to be something acceptable for our purposes, in particular, maybe democracy. And the bad news were that Arrow itself proved that no function satisfied these three properties when we have at least three candidates. When we have two candidates, we have other rules, such as the majority rule that satisfies these three properties, and symmetry, and so on. So these were bad news because this means that making rational and fair decisions, taking into account the individual preferences, were not as easy as we thought, and it could be even impossible. But at the end of the day, we have to make decisions. We have to agree collectively about what we have to do in many situations, in our parliaments, in our companies, with our friends. So we have to find solutions for that problem. And one of the solutions could be using other preferences. Why we have to use strict rankings without ties? We can use, for example, not complete rankings, in the sense that it could be a pair of alternatives that we don't have clear our opinions between them, so these two alternatives are not comparable. Or maybe the preferences could capture the idea of a preference, an alternative being much preferred over another, or the contrary, being practically equally desired, but only with a little difference. So maybe the preferences could capture this idea, and in these cases, we could agree and make collective decisions. We could also reject the independence of irrelevant alternatives property and substitute them for another one, capturing also the idea of rationality but being weaker. We could changing drastically the model, maybe, why not? But we, in our work, have focused on restricting the domain of individual preferences. What does it mean? It means that in many cases, the nature of the problem in which we are discussing and we have to take some decision, allowing any possible preference as input is not reasonable, or the preference doesn't make sense. So in such cases, if we take the domain as a subdomain of the domain as not the universal domain, the domain does not contain all possible preferences, all possible strict orders, then it is possible to aggregate. And I will use, I will expose you an example of restricted domain that allow aggregation of preferences. So consider the fourth most voted parties in Spain, ordered by left-wing parties to right-wing parties. And we say that a preference is accepted, or in this case is rational, if the preference is coherent with this order, the order of left-right parties. For example, here I have represent the preferences of a left-wing voter. In the x-axis I have the four parties, and the most preferred party is Podemos, that is in the number 4. The number 4 indicates in some sense the intensity of the preference. And the second one is PSOE, the third one is PP, and the fourth one is Vox. So the preference of this voter is coherent with this ordering, because it goes from the left to the right. We can consider also a right-centrist voter, in which the most preferred party is PP, the second one is Vox, the third one is PSOE, and the fourth one is Podemos. It is also consistent because there is no jump through any party. The preference goes from adjacent parties, and we will see the inconsistency in the last example, in which the most preferred party is PP, the second one is Vox, as before, but the third one is Podemos. So this jump through Podemos, through PSOE, makes the preference inconsistent with the ordering. Therefore, it will be PSOE. This is a way to, there is a way to express that type of preference formally, but I think that with these examples, the idea is more or less clear. And as a curiosity, the preferences are called single-peaked because the accepted preference has a peak or no peak in the diagrams like that, but the non-accepted preference have two peaks. So it can be seen that the domains containing all single-peaked preferences, there exist aggregation rules that satisfy the properties that I said before. And the question that we are addressing in our work is just that. Which are the domains D such that there is an aggregation function satisfying the three properties of the Arrovian model? We have seen that when D is the whole domain is not possible. We know that in specific domains, as the domain of single-peaked preference, the aggregation is possible, but there is no theorem characterizing which are these domains in which aggregation is possible. And this is one of the situations that I said before, that we have when we have many objects in this here. The set of alternatives can be bigger and the set of orders is much bigger. So combinatorics is not enough to address this problem. And until now, we think that topology could help us to solve that. And it's important to remark that we are studying this problem in the Rovien model, but this is a problem transversal in social choice, because in the whole area, preferences are used, and it in most of the problems, or in some problems, when we take the whole domain as the domain of the inputs, we cannot find good solutions or satisfying solutions to our problems. But when we restrict the domain, in most cases we can, but we don't know how to find this, which are these good domains that allows to find good rules to solve these problems of distributing resources or make collective decisions. So now, starting with topology, we are not the first ones using topology to address this problem. In the 90s, Yuli Barashnikov introduced a framework motivated to understand how the proofs, the different proofs of arrow impossibility theorem were related. And he used, as I will explain later, simplicial complex and simplicial homology. And the important thing is that he thought that there were certain topological invariants, in particular homology groups, encode the information of the preferences spaces in order we can discover, using the properties of these topology groups, these homology groups, which are the domains that are possible, in which are possible to aggregate and which we cannot aggregate. But under my point of view, one of the drawbacks of this approach is that homology is really, is something difficult, a little difficult for most of the economists, because they don't have the formation in topology and in particular in homology. So it's quite difficult to try to solve a problem in a community using specific tools that they don't understand quite well. So, yeah. First, I will want to give a little idea about the strategy followed by Barashnikov that I will explain deeper later. But Barashnikov wanted to transform the combinatorial structure into a topological structure. So they transformed the spaces, the sets of preference, into simplicial complexes, and the aggregation function that provides us the social preference given as input the individual preferences into a simplicial map. In order to illustrate in particular this transformation, here we have an example for three alternatives, A, B, C, all possible orderings of these three alternatives. And this set is transformed into this simplicial complex where every triangle represents a preference and every vertex represents a relation between two alternatives. For example, this one represents that B is preferred to C, because we have B and C, and we have this superindex B. I will develop later more technically. And this one says that A is greater than C, because we have this minus sign. And I have explained you this right now because I wanted to give you an idea about the complexity of the solution provided by Barashnikov, because their strategy consists on first computing the homology groups of the output space and the input space, specifically taking into account very specific generators that represents each one of the voters, because after he used this theorem that says that a voter is a dictator if and only if the image of the corresponding generator is the generator of NO. Otherwise, it is 0. So at the end, he had to prove that at least the image of one of these generators was 1, and for that reason, with that purpose, he used these combinatorial diagrams derived from the Pareto property, applied the homology groups, and studied these diagrams of homeomorphisms. So, as you can see, it's not something quite easy if you don't have a strong formation in topology, in algebraic topology. In contrast, we propose using a tool that is more simple, that is the index lemma from combinatorial topology. I suppose that most of you does not know the index lemma, but probably we are familiar with the, I think that is the Poincaré lemma. I'm not really sure about the name, but this result gives us information about vector fields. So if you have a vector field and a region limited by in this case a curve, we know that we can obtain information of the critical points inside this region looking only on the image of the vector field into its boundary, and looking how the image of this, looking on the image of this vector field, we will obtain information of the critical points and vice versa. So the index lemma is some kind of discrete version of this result. First, consider that we have an oriented simplicial complex consisting of a triangulated polygon, and we define two magnitudes. The first one, the content and the index. The content is the number of tricolored triangles labeled, the tricolored labeled with 0, 1, and 2. So if we have this orientation, for example, here we have a tricolor triangle and the orientation goes anti-clockwise. So since the orientation of, since the labelings of since the color of the triangle goes in this direction, 0, 1, 2, and is in the opposite and the opposite, and it is opposite to the orientation of the simplicial complex, then the contribution of this triangle to the content is -1. And we can do the same with the other two triangulations. So at the end of the day, the content is equal to -1. And we have another magnitude called index, that is the number of edges labeled 0, 1 around the boundary of the polygon counted by orientation. So we have 3 edges 0, 1, and the orientation of the boundary goes this direction. So this contribution is +1 because goes in the same, the 0, 1 goes in the same direction as the orientation. This -1 because it's 1, 0, and this also -1. So the index is -1. And the index lemma says that the index has to be equal to the content. As you can see, this result I have been able to explain you in a pair of minutes, and it is really easy to understand and to apply in contrast with homology groups. So we plan to, we have been using this result in order to prove the Arrow theorem with this topological approach instead of homology, and making some advances in the resolution of the restricted domains problem. So until now, well, our results are published in this. Well, this is a working paper that we are waiting for the publication, and this is a proceedings paper. So until now, we have first, in order to see that our approach is useful, we have proved the Arrow's theorem, the general, without domain restrictions, and we have proved for the base case, that means 2 voters and 3 alternatives, and we have used the base case because here the dimension is 2, and it is easy to draw the simplicial complex and see what's happening there, and we have some intuition. And after we have generalized we have generalized the result into the general case using a lemma that you can find in both of the papers, but it is not a topological lemma, it's only a combinatorial lemma. And we have also solved the problem of domain restriction, so we have characterized all the domains in which aggregation is possible, but only in the base case, just for that reason, because in this case, in the low dimension, we have some intuition about the geometry of the simplicial complex, and now we are working on applying these intuitions on the general case. So now I will go deeper into the math and try to explain briefly our results and the construction of the simplicial complex, how would you use the index lemma, and finally the results on restricted domains. So if you have any questions about mainly the framework of the problem, I can answer you now briefly, and if you don't have, I will continue. Okay, so I will continue with the math. So, well, I have said before, Baryshnikov needed to transform the structure, a combinatorial structure of the problem, into a topological one. And for that, transform every space of preferences into a simplicial complex, and this aggregation function, into a simplicial map. And how did it? He defined the vertices this way. He set a pair of alternatives and defined this sign and said that this set was the set of all preferences such that x is preferred to y. And he did the same for the minus sign, but the opposite, saying that this vertex was the all preferences such that x is less than y. Obviously, the set xy plus is equal to the set yx minus. And until now we have only defined the vertices, but we can see that all these sets is a covering of double B, and using, well, in a parallel, with the inspiration of using the inspiration as its inspiration, the covering lemma, we can build up a simplicial complex, saying that a set of vertices defines a simplex if and only if their intersection is non-empty. And as I presented you before, when we have 3 alternatives, we obtain this simplex, this simplicial complex, in which the simplex of maximum dimension are just the preferences. This one means B preferred to A, preferred to C, and the vertices represents the relation between a pair of alternatives. And I said before that this sign, the equality xy minus plus is equal to x minus. And we have, so deciding the superindex max plus or minus is only related to the notation, but we have decided to put the minus sign in the outside of the simplicial complex and the plus sign in the inside. And this is important on the proof that I will explain later. So even the index is only the sign is only a question of notation. This will be used later. And what do we do with ni, the set of profiles? We do the same. Here, instead of a preference, we have a profile or n tuple of preferences, one for each agent, and the superindex is a n tuple of signs. But it's defined following the same spirit. This vertex contains all the profiles such that the if agent, the if voter, prefers x over y if and only if their specific component in the superindex is plus. And we follow the same argument to build up the simplicial complex as before. And here we have a representation of of pieces of the ni and no. And here you can see why we have focus on the base case. Because we can draw the simplicial complex and obtain some intuitions. Here we have, on one hand, we have two cylinders, concentric cylinders, containing the inner cylinder contains the unanimity profiles. As you can see, the superindex, both agents coincide. In this case, both agents prefer A over B because the sign plus. And in the exterior cylinder, the preference of the agents are opposite. So the inside cylinder we call unanimity cylinder, and the outside cylinder we call anti-unanimity cylinder. And in this part, we have a mix of vertices being unanimous and vertices being anti-unanimous. So whereas here we have two cylinders, here is a torus that is identified with the cylinder according the blue edges and the green edges. So at the end we have two cylinders, two concentric cylinders with a torus glued between them in some strange way. That so if here is the representation is a little complex, but obviously is affordable. So imagine when we have a simplicial complex on, for example, the next one is 5 dimensions, I think. So it's really difficult to understand. So yeah, and well, we will continue. We will return on the simplicial complex later. But the final part is how Berezhnikov transformed the aggregation functions into a simplicial maps, and he used on this transformation the independence of irrelevant alternatives, because independence of irrelevant alternatives, if you remember, says that the decision between a pair of alternatives only has to depend on the individual decision of over the same pair of alternatives. So if we have, for example, the vertex AB plus minus, then we can say that it goes to the vertex AB, and the sign here will be the sign defined by F. So if the preference, so if the order AB for the first agent and BA for the second agent goes, for example, to AB by F, then here we will have a plus. And by independence of irrelevant alternatives, it doesn't matter where is C. It doesn't matter if C is here or if C is here, it doesn't matter. So the this F is well defined, thanks to the independence of irrelevant alternatives. The Pareto property sets the image of the unanimity vertex. And finally, saying that that there is dictatorial is equivalent to say that F is a projection. So the Arrow's theorem can be translated to this theorem only related to simplicial complex, saying that if we have this simplicial map such that satisfies this unanimity property, then F has to be a projection. And as I have said before, Berezhnikov proved it using homology groups. And the important part here is that, caused by that, the thing that I have said that he proved a theorem saying that an agent was a dictator if and only if the image of the corresponding generator was the generator of NO. He said that, he launched this hypothesis, saying that a domain allows aggregation if and only if the induced complex of D, following the rules that I have described before, is contractible. Because he get the inspiration saying that, okay, if the complex is contractible, then all homology groups will be zero, then no image of any of these generators will be different from zero. And he checked that hypothesis on the domains of single picket preference, that are the domains that I explained to you in the beginning, that in these domains allow aggregation maps. But we have seen with an example that this is not true. The hypothesis of Berezhnikov is not true. We have proposed this domain of preferences inspired in a polarized society. So we suppose that A and B, we have three parties. A and B are two right parties, and C is a left party, left wing party. So as the society is polarized, each voter can have to be a right voter or a left voter. So the most preferred have to be A and B or C. So at the end, it is translated to C cannot be in the middle of an individual preference. So we removing the preference in which C is in the middle, we obtain this space, and this is homotopically equivalent to that space, and as you can see, this space is not contractible. Whereas we can define an aggregation map satisfying the three properties of the Raventian model. So the hypothesis of Berezhnikov is not true, and this is another point that suggests us that working with homology groups might not be the best solution. So the final part, I'm a little out of time, but I want to explain you the broad idea of our proof. The idea of our proof is that we want to apply the index lemma. So we need to work to obtain information from a coloration of our simplicial complex. So we suppose that we have an aggregation function that satisfies the properties of a Raventian model, and we define a coloration over the vertices using this formula here. So the coloration of a vertex depends on two components. The first component is the identifier that is defined taking into account the sub-index. And the second one is define it as +1 or -1, taking into account the image of the vertex. So, for example, if we take this vertex and this vertex goes by f to u, b, c minus, no, plus, then the coloring will be defined first for the identifier, that the identifier is 1, plus the sign that is +1 because this sign on the image. On the contrary, if we take this AB that goes, for example, to AB minus, then the identifier will be 0, the sign will be -1, and this is congruent. This is the reason we put here the modulo 3 to 2. So using this formula, we obtain a coloration. And when we have a coloration, but this simplicial complex is not a polygon, so it is enough to take this band. Why it is enough to take this band? Well, this band is this band from here. It is enough because this band contains all vertices of Ni. So if we study the coloration of this band, in fact, we obtain the coloration, we are studying the coloration of the whole Ni, and then we know the information of the function f. And now this band, we can orient this band, and we can apply the index lemma. And yeah, I wanted to explain you the proof in case I had time, but I'm sure that I won't have. But the important part is that using the index lemma, we have proved that this function is dictated, well, the Arrow's theorem. And by the argument that I said before, and this is the most interesting part that have helped us to obtain the characterization theorem, as we have proved that in the band, only using the band, that the Arrow theorem is true in the sense that it is not possible to aggregate. We know that any simplicial complex that contains this band won't allow aggregation. And with a symmetric argument, we know that if the simplicial complex contains also this band, aggregation won't be possible. So in order to obtain a domain that in which aggregation is possible, we have to remove at least one triangle here, one triangle here, and one triangle here. And in fact, we have proved that only removing, for example, this triangle, well, we have characterized obviously the whole domains in which aggregation is possible, but only removing one triangle from here, and one from here, I mean one triangle on this band containing a blue edge, and one triangle on this band also containing a blue edge, but just this, that is the triangle that intersects the first one. Then, for example, we can remove this one, then aggregation is possible. So we have obtained the maximal domains in which aggregation is possible, and we have seen that these triangles doesn't play any role on the aggregation. So yeah, we have characterized all the domains in which aggregation is possible on the base case, and we have obtained a little intuition about what is going on. And the surprising thing here is that only removing a pair of profiles, aggregation is possible. So in this model, in the original Arrow theorem, it is not possible to aggregate but it's almost possible to aggregate because only removing a pair of profiles, the good profiles, but we can aggregate. So the difficulties that we have in our work now is that this we have the intuition for lower dimension, but the next case is, as I have said before, I think dimension 5, and it's difficult to imagine and drawing the simplicial complexes, but we think that with the help of the base case we will be able to do so. Our works now, is this one, obtaining a general characterization, and on the other hand we are trying to also to apply the same approach but using other framework of other framework. I mean a different problem in social choice that it's a little related to the other to the problem that we have studied, but the goal with that work is seeing if our approach can be used in general in social choice. And that's everything. Thanks for listening to me.
Well, thank you for a very interesting talk. The floor is now open for questions. I had a question. In one of your slides, you produced a situation where you were able to do an aggregation in something that was not contractible. You had some homology in it. So is this an argument that using the index theorem is more useful than using homology theory?
No. This is an argument saying that on one hand, the hypothesis launched by Berezhnikov is false, but this example is only for the hypothesis, but I have another argument in order to argue that in the characterization theorem, I have not said but I said that, well, let's remove that. Okay. Imagine that I have said that, for example, if I the domain defined by the whole domain except this triangle and this triangle allows aggregation function. And we have proved that. But what happens if instead of these two triangles, I remove this one and this one? You agree with me that in fact, both topological spaces are homeomorphic. However, the first one, this one with the light green allows aggregation, whereas this one does not allow aggregation. So, in fact, it's not. We have seen that the problem is not with homology. It's like, topology is not enough Topology itself does not contain the information of which domains allows aggregation or not. It is important to consider all the labelings of the vertices. So, in fact, it's not a poor topological problem that we are solving. We are solving topology plus these labelings. This is the reason behind we have using something, combinatorial topology, because we need the information encoded in these vertices, not only the topological spaces.
Okay, how about some other questions? Well, if there are no other questions, let's give the round of applause for a very interesting talk. Thank you very much.